Okay, so we're taking a look at another example from section um, 5.2. I forgot what section we were on. And so as we finished the last video by taking a look at what this meant when we have x sub 0 equals 1. And this is the same differential equation we had before, but the algebra is a lot different because of this shift of the initial condition. So let's see how that shift is going to affect our solution. So first off, we have to substitute in the sum from 0 to infinity of a sub n. We have x minus n minus 1 to the n power now instead of just x to the n. Okay, so then we want to make the appropriate substitutions for y prime and y double prime. Oops. And so there's the second derivative here. N times n minus 1, right, times a sub n, and then x minus 1 is to the n minus 2 power. And then we'll go ahead and substitute in for the next one and the last one. Good. Okay, and now you see where the problem is, right? Do you notice that we just can't bring this x in like we did before? Instead, I need an x minus 1. And so the idea here is I'm going to focus in on just this middle term, and I'm going to add and subtract 1 so that I have an x minus 1 that I can group together. Okay, and so we're going to focus on that second term, and I'm going to write, I need a minus x minus 1, right, instead of minus x. So I'm going to add and subtract 1, and so that means this is going to be equal to this term plus 1 minus 1. So I'm going to group these first two together so that I have an x minus 1, right, as a leading term in front of the sum, and then this one is just going to come along for the ride. Okay, notice that I'm factoring out that this term, right? So this is minus x plus 1 if you were to expand it. Okay, so I'm going to bring these first two things together to get the x minus 1 that I need, and then this term will just drop down. Good. And now this I can bring in, like I said, that was our goal, bring this x minus 1 into the sum, so this now becomes just an x minus 1 to the n power, and again this just drops down. Okay, so what I've done is I've converted this one term of the sum into two terms of the sum. Okay, so now we're going to bring these two terms back into our other sum, and so instead of having three terms we now have four. Okay, so this was our second derivative, right? And then these two terms here were the two terms that I just created, right? And this was our minus y here. Okay, good. And now we're all set. Now let's see, can I check to see what my powers are? So in this first term I've got x minus 1 to the 0 power, right? And in the next term of the sum I've got x minus 1 to the 1 power, and then the next one I've got n equals 1, so that's 1 minus 1 is 0, so that's x minus 1 to the 0 power, and finally the last term I'm starting with x minus 1 to the 0 power. So you see we have that odd one out here, the x minus 1 to the 1, and so I need to do something to that before I start. So what can I do with this n equals 1 here? Because of this one, because this is an n here, right, I can go ahead and take this from n equals 1 to n equals 0 without changing the sum. So I'm just going to shift that index on the second sum here, right, and now all of my indices start with the right number. And so now in this first sum I'm going to make my substitution. I'm going to say that k is equal to this power here, n minus 2. Here k will be equal to n. Here k will be n minus 1, and here k will be n. Good. So summarizing that, k is equal to n minus 2, k equals n minus 1, k equals n. Okay, sometimes it's nice to, right underneath of that, write down what your n is going to be, because that's really what you're going to be substituting into your expressions. So wherever I see an n in this first sum, I'm going to substitute k plus 2 in. And similarly, well, the second and fourth terms don't change. I'm just switching n to k. But the third term does change, right? The n minus 1 becomes a k, the n becomes a k plus 1, and that becomes a k plus 1. Right, so once I've made all my substitutions, looks like that. Good, and then I factored out the x minus 1 to the k power. And this is really what you want right here, this the single sum, where everything is x minus 1 to the k power. Because now what we can do is we can take this coefficient in front of the x minus 1 to the k and set it equal to 0, right? And that will give us our recurrence relation, and that's what we're really after here, is the recurrence relation. So we set our coefficients equal to 0. By the way, there should only be one coefficient. Excuse me. Ooh, shouldn't have had that cup of coffee. Let's see. I can factor out that 8 to the k power here, or a sub k, to get another minus k plus 1 in here. And so I'll just go ahead and solve this equation for a sub k plus 2. And that's what we always do, by the way. We always solve for the a with the highest coefficient. So a sub k plus 2 is always solved for in terms of the coefficients, the lesser coefficients here, the ones that came before. So that's what makes it a recurrence relation. So like k plus 2 depends on k and k plus 1. Good. And so this expression right here is called our recurrence relation. And we can just stop there and say, once we have the recurrence relation, we could figure out what the solution is, right? This is really the key to the solution. And so typically, like for an exam or something, we would just stop here. Good. We could write it out. I guess I'm going to go ahead and write it out. I thought I was going to stop there, but I see I've found myself having a little more motivation there. Okay, so a sub 2 you could write as this expression, a sub 3, and you could just write, if you were by yourself writing these out, you might go out a few terms just to see what it looks like. But then, as we mentioned in the last video, you can find a fundamental set of solutions, right, by taking different constants for a0 and a1. So 1, 0 you could do for one function and 0, 1 for the other. Do you remember why that is true? Why we can do that to find a fundamental set? Here's a hint. It has to do with the Wronskian. If it's true that y of 0 equals 1, y prime of 0 equals 0, and then for the second function, y of 0 equals 0 and y prime of 0 equals 1, the Wronskian between these two functions, y1 and y2, would be 1. And so that's why they form a fundamental set. Okay. That's the end of the presentation. I may do one more. I'll see how you guys are doing. I'll do the next one by hand so you can see what it takes to do one of these by hand. I did this by using a slideshow so that you wouldn't have to sit and watch me try to write all this algebra. So it does take a little bit of time. But the next one we'll go through together, writing it out from scratch. Okay, see you later.